displays. Is there anything you don't do with electric vehicles? That might be a shorter conversation.
Okay, let me see if I got, at least I can master this, maybe these slides.
If you can go 10 minutes, that would be great.
I'll do my best.
All right.
So I first want to say that all those subjects, there's a whole team of people here at our center now, and some young people who are doing a lot of work in this area. We do a lot of survey work on this market, both for California. Dr. Karani, and actually we have a lot of very new research, so I'm hoping I get a chance to speak again to you sometime, or some of these other folks. We're just going over.
We will.
Some new, very recent survey work just completed in the last few weeks, 2 studies of California, the rest of the United States. Both the general market, those who are not buying these vehicles, as well as those who are buying these vehicles. And we're also beginning a project where we're collecting, Dr. Nicholas is collecting a lot of data over the next 2 years from vehicles, sort of second-by-second data from 300 California households. So we'll know great detail how they use their vehicles. So let's see, am I doing this right? No. Oh, there we go. So first, I just want to start off. I do a lot of work on a global scale. This is a global market, so California is a big leader in that. But I'm going to talk a little bit today about the global market real quickly. I'm just going to start off by saying this is very early in this market. We are just starting. So we have about 4 years of data now, and if you're a statistician, if you have 100 years of baseball statistics, you can do a good job. But when you only have 4 years, you're just starting to understand what you're studying. So we have about 4 years of data. Here's some of the things that are happening. You can see that we have sort of a pie around the world with not many sales in Africa or Latin America or the Middle East, but Asia and especially China. I just got back from a week of work in China. Where the market is developing. One milestone's coming up, and that's probably sometime, maybe September, I think. There will be about 1 million plug-in electric vehicles, and that acronym covers both battery electrics as well as plug-in hybrid electrics. But that's only 0.1% of a billion vehicles in the world, so we're just getting going. The annual market in 2014 was about 300,000. I'm looking at, probably should exceed 400,000 this coming year. The market's growing a little bit faster right now in Europe and Asia, and they'll probably surpass North America as percentage of sales in this year. But still, that's only about 0.5% of the 88 million vehicles sold in the world. Sales are concentrated in a few beachheads like California, the west coast of the United States. California is, of course, a leader. Is about 9 to 10% of world PEV sales, but it's only about 2 to 3% of all vehicle sales. So we've got about 3 times as many as these other beachheads. So here's the governor's goals. You all know that. I think I'll just skip this. I was trying to adapt a little bit to this talk, some of my work, because most of the time I don't look out all the way to 2030. I study mostly 2020 and 2025, and I'm not actually a forecaster. What we do is study what's going on in the market and try to understand how consumers are responding to these vehicles. But here's what, trying to use some of what some of the other folks have gone ahead and studied. They're looking at wanting between 2.5 and 16 million ZEVs in California. These are big targets to achieve some of these. I'm just going to say and I'm going to go on a little bit of a limb here. We know we're legislating 250,000 zero-emission vehicles. Those are mostly plug-in electric vehicles, about 15% of California's market. And overall, this would mean about 20% market growth per year. Most of these studies, most of these goals, if we go out to 2030 also, if we're shooting, I'm going to use 5 million vehicles here as a goal. We're talking about 20% market growth per year. That's our familiar slide for the Air Resources Board showing that goal of 15% of annual sales. A lot of that coming from plug-in hybrids right now. Those numbers are probably under adjustment all the time, what those ratios are. So let's assume, and 5 million plug-in electric vehicles, a larger proportion we're probably expecting of plug-in hybrids, and some portion of battery electric vehicles from looking at the market. And maybe that'll replace about 1.5 billion gallons of gasoline. And this is where I got those numbers. You know, if we average vehicles today, that's a good average. That's a high average, driving what we think is about 12,000 miles, using 400 gallons a year per vehicle. That's 2 billion. But of course, in 2030, we'll have much more efficient vehicles. Electric vehicles compete in the marketplace with very efficient gasoline vehicles, which are coming into the market. So maybe it's more like 1.5 billion gallons we can expect. So if the fleet grew from 1.5 million PEVs, which is the goal of the state in 2025, to 5 million in 2030, you know, that's an ambitious goal. We're trying to understand from looking at how the market's growing right now whether that's possible and what you'd have to do to grow it. Here's what's been going on in California.
Let me just say that. Do you have an answer to that? What we need to do to make
that's where I'm headed.
Okay, great.
My last slide will be the bullet points on
all
that.
Right.
And I'll show you a little bit of. I'm not going to show all the survey work. There's just way too much to talk about today, and we're right in the middle of new analysis. So I'd like to save some of that. So what's the situation in California? You can see this growth curve. I mean, I can change of course, the chart to make it look steeper if you'd like. But that's, it's showing us growing to a few percentages. I'll talk about what's going on in the rest of the world in a second. California's annual vehicle market varies a lot. Right now, we're in a great market year. They're selling a lot of cars. It's almost 2 million vehicles in California. And sales PEVs are about 3% of that. You know, you don't get PEVs and pickup trucks and vans yet, maybe in the future, but not right now. So that part of the market, those buyers don't have that option. So another way to look at it is cars, and it's probably about 5% of cars. Year-to-date sales of 42,000 this year, PEVs in California. They had about 5,000 sales in May. If we went to the United States, it doubles that somewhat. California is 40% to 45% of U.S. sales. There are about 137,000 electric vehicles on the road in California, between PHEVs and BEVs, about split half and half. And there's about 25 vehicles in the market. This is about, out of models in California, this is under 10% of probably the models in California. So you don't have these available in every model yet. Here's some of the models that are for sale in the world. About 20 to 40 models are for sale right now of everything from plug-in hybrids with very small batteries that get 10 miles to up to 30, what we call extended range vehicles, which are focused primarily on electric, like the General Motors Volt. And actually, that's going to change here. BMW has a vehicle which is mostly electric. Battery electrics we're very familiar with, like the Nissan Leaf, and then up to the Tesla, which has very extended range. We have an infrastructure we're trying to roll out. We have a lot of charging. This is always a classic charging pyramid. Shows that most charging happens at home on what we call level 1 and level 2, which is 110 volt or 220 volt. Workplace has that level 1 and 2, and then there's these very fast chargers in public along corridors and a few other places, which are higher powered DC fast charging. Is 30% of market. 600 to 700 would be 600 to 700,000 vehicles per year. Is this possible? 5 million vehicles. Can we get there? Possible or probable? So let's look around the world a little bit. Japan, and I'm going to talk about hybrid vehicle sales. Over a 16-year period, they achieved 20% sales of hybrid vehicles in Japan. That was done with incentives over almost that entire period, sales tax reductions as well as other incentives. A very motivated hybrid auto industry in Japan, which works very closely with the government. But that was what was one place possible. So that gives you a little reference. Not as difficult as PEVs because we have to build an infrastructure. Norway, though. Let's look at Norway. This is a very interesting small market. extremely high incentives. I like to call this, sort of a Viking alchemy. Somehow they're turning oil into electric vehicles here. In Norway, they have oil, and they use a lot of that money to pay for incentives and infrastructure, and they already have a 20% market there in 5 years. Very impressive. It's because an electric vehicle is cheaper to drive there. Netherlands, about a 5% market. Mostly plug-in hybrids, a little bit different than Norway, has different incentives. Very aimed at company cars, which is not a big market in the United States, very big in Europe, especially Netherlands. California, ZEV programs, here we're getting to 3% of market, 5% of cars said, maybe 10% somewhere like San Jose. People start to see their neighbors have these in San Jose. China, it's shooting for California rates. They're putting in place probably ZEV programs that will achieve similar rates to California. There's a few other 1% markets: France, Japan, UK, Denmark, Iceland, Estonia. Some odd ones, some small markets. They're getting about 1% sales with about $10,000. Germany, no incentives, a very motivated auto industry now, but about half that rate. So the development of the market, I just want to talk about quickly again. I mentioned Japan. This is how they did it. Looks a lot like where we are right now in California up to 2004. They doubled that market, and so did California at a lower rate for hybrid electric vehicles in, over a 5-year period. And then, and what's important about this 3 phases I show here is that for auto companies, they tend to phase technology development in 4, 5, 6 year chunks as they come out with new models. A lot of you might remember that big change to hybrid vehicles in 2004 when the second generation Prius came out, quite different. The vehicles improve at least 10% per generation, and then hopefully by the 3rd generation, your costs of your vehicle are leaned out. And that's when you start to make profit. But as Tim said, there was no profit probably till this 3rd generation for hybrid makers. I just went over all that. Okay, so I'll go to this. This shows you some hopeful news about this. This just shows you that actually for plug-in electric vehicles, if you compared the first 36 months of the hybrid market to the first 36 months of the PEV market, we're actually moving faster than hybrid markets moved, considerably faster. Although you might want to split PEVs into plug-in hybrids and battery electrics. Sorry.
Could you keep that up for a little bit?
Sure.
So the dotted line is
the sales, and the solid line is the accumulated vehicles. So you can see the accumulated vehicles is over on the right, and the monthly sales figures are on the left, which is the dotted lines.
All right. So
this is for the United States.
All right, and then the red is the initial rollout of the hybrid electric
over
vehicles.
its first 36 months. So you're comparing not the same time period, but the first 36 months of each.
Okay, so the hybrid electric,
Yeah.
which basically it was an efficiency, not a...
It's efficiency.
Yeah, it's
There
not
were
really a
some
range
incentives.
issue.
There were incentives, fairly strong incentives in Japan, weaker incentives in the United States, but sales incentives federal tax credits were available. So that's why I use the 36 period, which the tax credits ran out for the hybrids at that point.
And a very large fraction of that rollout is in California in both cases?
About 1/3 of hybrids were in California.
Okay. And
Similar to what we're doing now.
okay. All right, go ahead.
So this is Tom's model up to 2025 based on using that hybrid model, what we know from diffusion models of new product rollouts, understanding OEM product rollouts. So we tried to understand this. This shows us, I haven't gone to 2030, but I'm going to show you this, which gives us the 5 years we're in right now. We're at the market, we're actually ahead of this model, and we're expecting to double this up through 2020. Here we'll have second generation vehicles, and we'll be refining and expanding our infrastructure. This is what I'm thinking we'll expect. This is not a forecast, this is just a model based on this history. And finally, we should expect in between 2020 and 25 some leaning out of the cost of the vehicles, third generation vehicles, which are greatly improved, and maybe even grid integration here in California, where the charging of the vehicles will be integrated into grid functions.
So what are the numbers? Oh.
What are the numbers?
Well, on 2025,
That's 250,000. That's 1.5 million plug-in electric vehicles I'm expecting. Similar to the ZEV number. It's very close.
And that's with current incentives, current policies?
I would, if I use the hybrid electric vehicle, I think incentives will have to extend at least up into the somewhat into the third generation if we use Japan as a model. Prices will lean out during that third phase, but there will still be some higher costs, as you heard from E3s of the vehicles. Battery prices are coming down faster than experts thought right now, but they will still probably exceed, kind of break-even prices. Maybe up around 2025. Some people think you could, if it goes far enough.
Your recommendation is if we want to get to 1.5 million, we've got to continue some of the current programs, maybe all of them.
Programs, yeah.
All right.
I think we would expect the need to keep some in place to attract new buyers.
All right.
Keep growing the market.
Okay, go ahead.
Here it just shows you one of the things we look at closely, and that's just the knowledge and experience of buyers. This shows a recent survey of 6,000 Americans. We have a sample of 2,500 Californians on this. It just shows that this is just very simple. If you look over on the left-hand side, just shows these are people that tell us they have no experience with these vehicles. Here's the number of people who have some experience, the kind of experience you need to make a purchase decision. Usually the only people who make a purchase decision without this kind of experience are more adventurous buyers, what we call early buyers or innovative buyers. Those are people who, without much experience at all, will go down and buy a car and test it out. But here just shows you we have a long ways to go in terms of consumer education. This shows you how incentives, the response of drivers, it varies across some of the vehicles. This is from a recent survey in the United States, the impact of federal incentives. It just shows you some cars. Shows that buyers who would still buy the same vehicle if the incentive went away, or they'd buy a different type of vehicle. It shows a large number of people say, especially if you look at the very loyal buyers at Tesla, they would go ahead and they purchase the vehicle without the federal incentive. But we do have a lot of people right now who wouldn't have made that purchase.
So the percentages, so the blue line means what?
They'd do it again.
They'd do it again, and that's plug-in electric.
The next one said they'd probably go to a hybrid, or if they didn't have the incentive, they'd go to a ICE or a hybrid. And the other people said...
internal combustion.
Internal combustion, I'm sorry.
Right.
And then finally, the last people said, I wouldn't have bought a car at that time. Maybe they'd wait and see what happened.
All right. So it's the newer models that are on the bottom here that have the least...
Well, if you look at the top, it includes all of them. You can see that about almost 2/3 of buyers say they'd do it again, but we would lose sort of much. So to remember with incentives, the important part is incentives aren't necessary for everyone, but they're very necessary for expanding the market from what you have now.
Right. At some point, if we can talk quantitatively about what sort of incentives we need to get to 5, 6, 8 million, I don't expect you to have an answer right now.
I think we have a lot of survey data on that, and Dr. Gil Tall would be a good speaker on that topic.
Okay, so let's make sure that we hear from you again on that. Okay. Is there anything else? You got a final slide?
I'll just go to this is about infrastructure. This shows people who are experiencing congestion at work because they're having trouble charging at one point. What we worry about in building infrastructure is the issue of congestion, that people show up at chargers and there's no place to charge. Somebody else is occupying that charger. And so we're worried about keeping ahead of that curve. This just shows you in a number of states where we've been surveying where people, if you look at California, people are encountering congestion at chargers now. So this is very discouraging for them. This means with plug-in hybrids, they aren't going to charge. It means with battery electrics, they may not drive it the next day.
Okay.
So what's had to be successful? We still, as I said, we need incentives. There's strong evidence from around the world. All those nations where we saw beachhead markets do have some sort of incentives. These broad sets of incentives in Norway. everything from parking lot, discounts to going to parks, to bridges, toll roads, just keeping the playing field a little bit in favor of zero-emission vehicles right now or plug-in vehicles. We also need, because it's an international market, to increase market share, you've got to develop these sort of international coalitions of the willing to set goals and work together. We do need a convenient and low-cost infrastructure, and we need to avoid congestion in that system, make it easy. And as I said earlier, we do need some sort of public education campaign to ensure diffusion of knowledge and experience here. We need more experience in the buyers. We need some sort of public campaigns and consumer education to keep this rolling. That's it.
Okay. I have asked my questions as you've gone along. First, let me introduce Assembly Member Autumn Burke. The two of us have quite a bit of interest in energy. We've been briefed by the CPUC on energy issues. And Assemblymember Burke, would you like to make some introductory remarks and then perhaps ask some questions?
I don't know that I'll just use my question as kind of my introductory remarks. I guess my concern in a lot of this conversation is I have a district that is Tesla drivers, and then I have a district that has no access to any infrastructure or any opportunities to charge an electric vehicle. And so I've been always of the opinion that for any of this to be plurality, we would have to include all communities. My question, I guess, for you is, has any of that been taken into consideration in any of this report? Any sort of secondhand incentives for secondhand vehicles or infrastructure for the eastern portion of these, there's some of these not so coastal areas that can afford Teslas and all these wonderful things. Is any of that taken into account in the opportunity to reach our goals?
We're in the middle of a study with the Air Resources Board that'll be a year-long study of the used electric vehicle market. We've just begun that because sort of the first leases are coming up right now. So we're tracking the prices of those vehicles with an economist at Davis, and we also are studying, doing survey work to understand who's buying those, how those are moving through the used vehicle system, and how are those vehicles performing. This is the first generation of vehicles, so I'm kind of cautious about this because these are initial vehicles, how the batteries perform. I don't want to saddle people who need a good used vehicle to get to work with an electric vehicle right away. This is a difficult issue, but I understand the parity, so we're trying to understand best how to move that forward.
Great. Other questions? Well, you've illuminated us a lot. I suspect that this light-duty vehicles is going to be an extremely important part of reaching that goal. And I won't say that you can make a perfect prediction, but your best guess as to what we need in the future should help guide us, both in terms of where you get it, how you get charging, and what subsidies we might need for that, as well as what subsidies on the vehicle. So this is something that we should be looking at in the next year and in years to come. So thank you very much for this great presentation.
We'll have some much better resolution this fall.
That'd be great. Thank you. Now we're going to talk about biofuels. One of my favorite institutions is the Joint Bioenergy Institute, which operates with Lawrence Berkeley Lab as well as with Caltech and I'm sure other institutions. The person who is coming from that is the Associate Director for Biosciences at Lawrence Berkeley Lab, Dr. Jay Kiesling. And he's the Chief Executive Officer and Vice President of Fuel Synthesis at the Joint Bioenergy Institute. Dr. Kiesling's focus is on engineering microorganisms to produce fuels and chemicals to replace products currently derived from petroleum. He's a pioneer in the emerging field of synthetic biology. His research focuses on engineering microorganisms to introduce useful chemicals. During the early 2000s, Dr. Kiesling led a UC Berkeley research team in engineering yeast microbes to synthetically produce artemisinin, the powerful anti-malarian drug. Researchers at the Joint Bioenergy Institute are now using the same technology to produce cellulosic fuels. His expertise includes engineering pathways for high-level and large-scale production of hydrocarbons, using functional genomics to characterize engineered organisms, and developing biological components and host cells for production of small molecule biofuels. It sounds like a lot of fun.
It's great fun.
Yeah, and you're smiling. I can tell it's fun. You've done some great science work, but what we really need to hear today is, as we've heard with the other people, is to know sort of timelines, where things are going. Are there things we need to do on a state level to, develop incentives? What are the best pathways? And if we could concentrate on that in your presentation, and I'll ask it to be for 10 minutes, which has been averaging about 20, but we have plenty of padding in this, so it'll be okay. So, Dr. Kiesling, please go ahead.
Great. Thank you very much for inviting me. It's a pleasure to be here. You heard a lot about biofuels from some of the other speakers today. And so I'm going to tell you a little bit about the science behind that, and then we'll get to some of the timelines and needs. So I don't have to tell you, we get almost all of our fuels and a lot of the chemicals we use from petroleum, and that puts carbon in the atmosphere. We'd like to replace at least the fuels part of that with a renewable resource. And there are many routes to this, but we grow plants in the field. Those plants take carbon dioxide out of the atmosphere to make the plant, and then they make it in a form of sugar, either sugar cane or starch in things like corn, or cellulose in things like grasses. We then refine that and make it into the fuels that we could put into our automobile. And because we're burning the fuel and putting the carbon back in the atmosphere and the plant's taking it out, we have the potential of having carbon neutral fuels this way. Now, this plot shows the amount of energy that you can derive from various different plants, shown on the left there. And at the bottom is the net energy out. So that means the amount of energy it takes to produce the crop and the amount of energy out that you get out of that crop. So the greatest energy out relative to the amount of energy input is sugarcane in Brazil. This is where they're making a lot of ethanol. Corn in the U.S. is just barely positive, maybe by just a few percentage, and that depends on the assumptions in the model. But the difference between the just barely positive energy out of corn and the eightfold energy that you get out of sugarcane is pretty significant. Switchgrass or cellulosics in the U.S. Gets closer to sugarcane in terms of 4 times the amount of energy out versus the energy in. Now, in terms of the capacity we have in the U.S. for producing fuels, this comes from an update of a report that you heard about earlier in one of the earlier talks, the billion-ton biomass report. The projection from the U.S. Department of Energy and Department of Agriculture is that somewhere in around 2022, 2030, we could have upwards of 1.3 to 1.5 billion tons of biomass. And that would come from agriculture, so energy crops in green, from forest lands and existing food crops where we could take the biomass that isn't used for food and use that to produce energy. Now, 1.3 billion tons of biomass gets you to about 1/3 of total transportation fuels used in the U.S. To grow that 1.3 billion tons of biomass, you'd need about 100 million acres. In the U.S., we farm on the order of 450 million acres, so it would be less than a quarter of that. Now, biomass is complicated. And I'm going to tell you just a little bit about that so that you understand the process of how we get the sugars out. So this is a typical plant cell. After the plant has dried, the plant cells are in here, and what's left over is the secondary cell walls. And those are really complicated, but they're made of primarily 3 components: hemicellulose, 5 carbon sugars; lignin; and cellulose, the 6 carbon sugars. And the lignin is a polymer that we can't readily use right now, but we can use the sugars in cellulose and hemicellulose to turn them into fuels. Now, if you look at any plant, it doesn't really matter what plant you look at, whether it's a tree or it's a grass or a flower, it's roughly 2/3 sugar. And that 2/3 sugar we want to turn into fuels regardless of what that plant is. So in order to get those sugars out of the plant, we go through a pretreatment process that extracts the sugar-containing polymers from the plant, and then we add enzymes to break down those sugar-containing polymers into the sugars, and then we feed those sugars to microbes that ferment them into fuels. So it's a complicated process, but it all goes on inside this biorefinery. Now, there's some challenges. We'd like to have as much sugar in a plant as possible. The best sugar-containing plant, as I mentioned, is sugar cane. Cellulosic biomass could be comparable to that, but we need even more sugar in those plants. We'd like to have pretreatment processes that are as simple to use as possible and that give as clean a biomass as possible that's uncontaminated with this lignin polymer, which we really can't use right now. The enzymes that we use to process cellulosic biomass into component sugars add anywhere from $1 to $2 to every gallon of fuel. $1 to $2. That's a huge cost. We need to cut those costs substantially. And finally, we need more than just ethanol. Right now, the cellulosic plants produce ethanol. Ethanol is great as an oxygenate in gasoline. We can use it up to 85% in a flex fuel car, but we can't use it as a jet fuel and a diesel. So we need substitutes for those. So the Joint Bioenergy Institute was started to do basic science. It's funded by the U.S. Department of Energy to tackle this entire problem because all of these challenges along this pipeline are interconnected, and a solution to one of these can solve a problem upstream. We brought together 7 institutions. Berkeley Lab leads the partnership with UC Berkeley, Sandia National Laboratories, UC Davis, the Pacific Northwest National Laboratories, the Carnegie Institute for Science, which has its plant biology department at Stanford, and the Lawrence Livermore National Laboratory. And we brought them all together at this single location in Emeryville. We're funded at $25 million a year by the U.S. Department of Energy. We were started in 2007 and renewed in 2012. Let me just talk about how we've tackled some of these challenges. So I mentioned that we'd like to have as much sugar in the plant as possible. And there's these holes in the plant when it dries up and we take it into the biorefinery. If we could fill those holes up with sugar, we could produce more fuel from a given amount of plant or a given amount of land that we use to farm that plant. So we've engineered the plant. We've gone in and changed the genetics inside the plant. The first test is, does that plant grow? And you can see that it grows just fine, the engineered plant, relative to the plant we started with. But does it have more sugar? Well, here are the holes when we started. In the unengineered plant, some of those can carry nutrients, but some of them are just holes in the plant that we could fill up with sugars.
What kind of plant?
In this case, it's an Arabidopsis, but we do our experiments first in Arabidopsis. It's a model plant, and then we translate them into switchgrass and into things like rice, which is a food crop, but also we could use that extra biomass to produce fuels and still have food. So in filling up those holes, you can see we've got much thicker cell walls, and we nearly double the amount of sugar that you can get out of that plant. Another important challenge is the pretreatment process. I mentioned that this is a very expensive process. We have to get very clean biomass out in order to produce a lot of sugars. We've been using something called ionic liquids. It's a solvent that works very well to dissolve the biomass, and when you add water back to it, you get very clean cellulose and hemicellulose out. And it reduces the cost of those enzymes that, remember, was $1 to $2 per every gallon of gas or fuel produced, reduces it 90%, so down to 1/10, anywhere from about a dime to 20 cents for the enzyme. So huge reduction in the cost. Now, one of the things we've been experimenting with lately is, can we take this lignin that we might otherwise just throw away or burn to produce heat and make ionic liquids out of it? So we essentially get those ionic liquids from the biology for free. We call these bionic liquids, and it turns out that they work just as well as the ionic liquids that come from petroleum, and they would be essentially free to us. Now I want to talk about this last challenge, and the last challenge is, can we produce fuels that would mimic the fuels that we currently use in our automobiles today? We've been hearing a lot about changing out our infrastructure, changing out all the filling stations, changing out the engines. What if we could just use all of that infrastructure that we have? In the U.S., that's about $3 trillion worth of infrastructure. We're at a point with the biology where we can change the biology to produce fuels that mimic the fuels we get from petroleum rather than changing out the infrastructure. And that's what we've been doing. We've been engineering microbes that take in the sugars, and rather than turning them into ethanol, they turn them into hydrocarbons that behave exactly like the hydrocarbons we get from petroleum, so that we can substitute them directly as gasolines, as jet fuels, and as diesel. And I'll just mention that in some ways jet fuel is the lowest hanging fruit. It's unlikely that we're going to have battery operated planes anywhere in the near future. And so we need energy dense fuels, and hydrocarbons are one of the best ways to carry hydrogen because they are so energy dense. And we can produce some of these fuels, and fuels from microbes that were developed in my laboratory and in other laboratories have been fueling planes on various missions and buses in Brazil. Now, an additional feature of these hydrocarbon fuels is that, unlike ethanol, which is like making a mixed drink when you ferment it, you have to add a lot of heat to get the ethanol out in a pure form. With these hydrocarbon fuels that are made by microbes, it's more like making a vinaigrette, and that is, you add the vinegar and oil together and you put the bottle back down on your table, and they separate. Well, the same case with these phase separate. And you can see that the diesel floating on the top here, these are diesel blebs, and these are the little E. coli that are excreting the fuel made from a sugar source. So it makes the purification process significantly cheaper.